Okay, so in the last video we developed the rules for the 6 trig functions, the rules for the derivatives, that is, of the 6 trigonometric functions. So we're going to use those now combined with other rules, right? Constant rule, constant multiple rule, sum, difference, product, quotient, etc. And let's find the derivative in each case. So we start with this function g of x, and we're going to find its derivative. So what am I going to have to use to find the derivative of this function? Certainly we see the sine of x, so we're going to use one of our new rules, but notice we have a product, and I'm going to look at 4x cubed times sine of x. There's our product rule. Okay, and so when I go to find the derivative of this function, two functions, right? First times second, take the derivative of the first one times the second plus the first times the derivative of the second. Now, when I take the derivative of the first one, what is the derivative here? Well, what are we using here? We got a constant multiple rule, pull the 4 out. X cubed is power rule, bring the 3 down, and subtract 1. And so I get 4 times 3, I get 12x squared. Most of you can hopefully at this point do that very quickly. And then the derivative of sine of x, we derived it in the last video. Do you remember what that is? Cosine of x. Right? We proved it was cosine of x. So there it is. Our result comes out to be 12x squared sine of x plus 4x cubed cosine of x. I'm going to leave it like that. Maybe some of you might say, hey, I can factor 4x squared out of that. You could. But we're just going to take the derivative right now. We're not going to do anything with it, so no need to go there. But keep in mind, product rule is important. A lot of students will forget. They'll just take the derivative of this thing. They'll just do 12x squared times the derivative of sine of x, cosine of x, and they multiply those together. That is not the derivative. Okay? Use the product rule. All right, let's take a look at this one here. What rule do we have to use on this one? I see a cosine t and a sine t, so we got our new rules for those functions, for their derivatives. Hopefully you're saying quotient rule. All right, so we've got a quotient rule in here. So we're going to find dy dt if y is equal to this. And I can't really, if I could simplify quotient, right, I always try and do that maybe. But since I'm dividing by 3 sine of t minus 5, there's really not a lot I can do. Can't break this up into 2 fractions. No, that's not going to work. Can't simplify it any other way. No trig identity really helps out here. No factoring, nothing. So we're just stuck with it. So the derivative of y with respect to t, so remember this is the Leibniz notation for the derivative of y with respect to t, is equal to what? I take the derivative of the top function by the quotient rule, which is cosine t, times the bottom function minus the top function times the derivative of all of this in the bottom. All of that, remember, is divided by the bottom function squared. So what do we have? Well, we have the derivative of the cosine function, and what was that? Derivative of cosine of t was negative sine of t. Yeah, and so you're going to memorize these. Certainly you want to know the derivative sine of t is positive cosine of t, but the derivative of cosine of t is negative sine of t. So sometimes students get those signs mixed up, so make sure you really practice that. If you're in doubt, remember you can look at it as we looked at it in the last video graphically. Just look graphically and see if indeed the rules, the derivative rule you have matches up. In other words, when your function is increasing, is your derivative indeed positive? When your function is decreasing, where the slope of the tangent line will be negative, is your derivative negative? Okay. Derivative of this thing here is what? Well, 3 is a constant multiple pulled out. Derivative of sine of t is cosine of t, so it's 3 times cosine of t. And the derivative of 5, 0, minus 0. So it's just 3 cosine t. And so what do we get here? I'm going to go ahead and distribute now. Indeed, this is negative sine of t times these two, so I'm going to distribute those through. Negative sine t times 3 is negative 3. Sine of t times sine of t is sine squared t. And then negative sine of t times a negative 5 is plus, right? 5 sine of t. And then minus cosine t times 3. Cosine t is 3 cosine squared t, minus 3 cosine squared t. So simplified that. Well, can I simplify that? Can I combine any like terms? No. But there is something I can do. Does anyone see something very interesting there? Kind of like this guy and this guy. Yeah. I can pull those two together. I'm going to pull them to the front, so to speak. And both of them have a negative 3 factor. I can pull that negative 3 factor out of those two expressions. And what am I left with? Sine squared. I pulled a negative 3 out of here, plus, right, cosine squared t. I still have this plus 5 sine of t. Don't forget that's floating around there. So remember, I can change the order I'm adding things. You might say that's subtracting, but I can think of, minus 3 cosine squared t is really what? Plus a negative 3 cosine squared t. So I can change the order I add in. And that's what I've done. I moved this guy over here in front of the 5 sine t, moved the 5 sine t to the end, and then out of these two terms I factored out that negative 3, leaving that. And hopefully you see that, and you know what that simplifies down to in the parentheses there. What is that? What is sine squared t plus cosine squared t equal to? That's just 1. By what? The Pythagorean identity. We used that in the last video as well. And so what do we have here? We have negative 3 times 1. That's negative 3 plus 5 sine t over 3 sine of t minus 5 quantity squared. Kind of a weird, interesting result. And that's about all we can do. You could rewrite this as 5 sine of t minus 3 if you want to. It doesn't really change anything though. But there's no common factor. Be careful, this is not the same factor, right? 3 sine of t minus 5 is not 5 sine of t minus 3. It's a little close, but not quite. And so there's not a whole lot more we can do. Should you expand out the denominator here, FOIL this out and do all that? Not really. I would leave it in that form. I wouldn't expand that. The only time I want to simplify it, right, is if you have common factors. So you want to leave the denominator factored. If you have a common factor with the numerator after you simplify the numerator, then yeah, you can simplify that down. But that's our result. Now, in general, when you start taking derivatives involving quotients, products and quotients of trig functions, for instance, with other types of functions, you can get some pretty strange looking results, some convoluted looking expressions for the derivative, and that's okay. But if you just sit back for a minute and start from the beginning, if we had this problem from the very beginning and said find the derivative of this function, using limit definition, you would be going crazy. Trying to use the limit definition on this would be a nightmare. But because of the, we've analyzed and looked at the derivative of these individual functions, we looked at the quotient rule, looked at the sum difference rules, constant multiple rules, all those. Now it's much easier in comparison to what it could have been. So, and we can do some very hard derivatives now. Let's do a couple more. This one's fairly simple, but you do have to know the rules for the derivatives of tangent and secant. So notice I have a difference of two functions, so the derivative will be the derivative of each one, and then subtracting. And then each one has a constant multiple. So when I look at h prime of u, notice u is the independent variable here, u is the input. So the 7 comes out, and I want to take the derivative of tangent u, and then the 6 comes out as a constant multiple, and I can take the derivative of secant u. Now what is the derivative of tangent u? Do you remember that one? We proved that one in the last video. There's lots of ways you can write it. The way we're going to write it, though, typically is secant squared u. That's secant u times secant u, or secant u squared. And the derivative of secant u is secant u times tangent u. We proved that one as well. And so the answer is simply 7 times secant squared u minus 6 times secant u tangent u. I'm going to leave it like that. Again, some of you say, hey, there's a common factor of secant u I can pull out of that, factor out of it. You could. It's true, but not necessarily here. We're not really doing anything with the derivative, just getting it, right? Getting it. If there's any obvious simplifications, trig identities, like the one we saw in the last example, the Pythagorean identity that pops out, you certainly want to simplify that. Combine like terms. Don't leave an expression with something like the square root of 4 or 0 divided by 1. Make sure you simplify those obvious, do those obvious simplifications. Combine like terms, do that. Okay. So you do need to remember there's also derivatives of the cosecant and cotangent functions to remember. Now, look at number 4. What in the world is this be asking me to do? What is this crazy expression? You want to remember what that is? That's the fourth derivative, right? This is Leibniz notation for the fourth derivative of p with respect to theta. P is a function of theta. What's its fourth derivative? So what do we have to do to get to the fourth derivative? Well, we have to start with the first derivative, which is dp d theta. What's the derivative of cosine theta? That is negative sine of theta. Okay. So now we're going to take the second derivative. How do I write that? That's d squared p d theta squared. That's the second derivative of p with respect to theta. And so how do I do that? I take the derivative of the derivative, right? The derivative of this function now. Well, I've got a negative sine of theta. What is this negative? This is negative 1 times sine of theta. So pull that negative 1 out. And what's the derivative of sine of theta? The derivative of sine of theta is cosine theta. And then multiply it by that negative 1 gives me negative cosine of theta. Okay? Well, getting there. Third derivative of p with respect to theta is written this way. That's the Leibniz notation for the third derivative. We say d cubed p d theta cubed. And what is the derivative of the second derivative? That's going to tell us the third derivative. Well, constant multiple of negative 1. Again, pull that out. What's the derivative of cosine theta? Remember, that's negative sine theta. We just did it up here going from the original function of the first derivative. But then multiply negative sine theta by negative 1, and we get positive sine theta. Wow. Well, one more to go. Take the derivative of this, and we'll get the fourth derivative that we're looking for. And that's the way we write it. What is it? What's the derivative of sine of theta? What's the derivative of sine theta? Cosine theta. What? Wait a minute. The original function. Are you serious? What? That's crazy. No, that's the case. And in fact, I think you see the pattern that's going to develop. We are in a vicious cycle, as it were. If I continue, and I wanted the fifth derivative of the function p, where am I going to be? Right back to here. Here's the sixth derivative, here's the seventh derivative, here's the eighth derivative of the cosine function. Ninth derivative, 10th derivative, 11th derivative, 12th derivative, and so on. That pattern just keeps repeating over and over. Just cycles between these four functions over and over and over again. Okay. Now, there's a neat little memory tool that I don't know, some students like to use. I'm not big on memorizing things per se. I would rather you understand how we obtain these. But it is imperative to know the derivative of cosine is negative sine theta, whereas the derivative of sine theta is positive cosine theta. And so that's often confused a little bit. And there's ways you can do that by looking at the graphs. I would encourage you to do that. But this is a little memory device. If you remember the unit circle, here's the coordinate axis in the unit circle. Cosine of theta is positive in the over here in the first and fourth quadrants, but cosine of 0 is positive 1. But I'm going to write cosine theta here, positive cosine theta, and then back here, right at pi. If you think about pi, if you think about the unit circle, I go around pi units or an angle of pi radians, then the cosine of that, its x coordinate is what? Negative 1. I'm just going to say negative cosine theta. In other words, I'm saying in these two quadrants cosine is positive, in these two quadrants cosine is negative. Well, for sine, it's positive what? In the first and second quadrants up here, right? Angle theta of a central angle for a point on the unit circle, then the y-coordinate is always positive, right? The y-coordinate is positive, sine is positive. Down in these two quadrants, sine is negative. Okay, so I'm just doing a little way of remembering how to find the derivative. If you now go in a clockwise direction, you will see the derivatives appear. And what I mean by that is the derivative of sine of theta, go clockwise, is cosine theta. Derivative of cosine theta is negative sine theta. Derivative of negative sine theta is negative cosine theta. Derivative of negative cosine theta is sine theta. But most importantly, it tells you derivative of sine theta is cosine theta, derivative of cosine theta is negative sine theta. I don't know, some people like this, and it is helpful if you go into calculus 2, because in calculus 2 we're going to sort of do antiderivatives, which is to go in the opposite direction. Okay, so in that case you'll be going counterclockwise to find antiderivatives, and that just adds another wrinkle on it, but you don't have to worry about that yet. Okay, let's do one more example to close with, shall we? We could do a lot of examples, but you just need to practice a bunch of them. Here's one more. Find the derivative of this function. Here we got a sine of x again. I've got an e to the x and an x, and so notice I've got a product. So I've got a product rule, but notice how many functions I'm multiplying together. 1, 2, 3, x times e to the x times sine of x. Do you remember when we did the product rule, a little quick way to find a derivative of a product of 3 or more functions, or 3 functions? Let's see if you remember that. It's going to be the derivative of the first function times the other 2 plus the first times the derivative of the second times the last plus the first 2 times the derivative of the last. Okay. Now we developed this rule, and that's the case. If you have a product of 10 functions, right, and you want to find its derivative, you take the derivative of the first function times the remaining 9, then you take the derivative of the second function times the derivative of the other 9, third function times the other 9, derivative of the fourth function times the other 9. Do all those products, add them all up, and that's your derivative. Okay? Or you can think of the x e to the x as being one function, sine of x as being another. Use the product rule on that, but then when you find the derivative of x times e to the x, you're using the product rule again. That's sort of the way we did it. So you might want to look back at the product rule video that I did to refresh your memory on this. The derivative of x is 1 with respect to x. The derivative of e to the x, what's that? Easy rule, e to the x. And our new rule, derivative of sine of x, is what? Cosine of x. And so our final result is 1 times that plus, well, this is just x times e to the x sine of x, and then this is what? X e to the x cosine x. And there's my answer. Again, you might see a common factor of e to the x you could factor out of this, but that's okay. I'm going to leave it just like that. Okay, so we've done a few more examples then using these new rules that we've developed. And we've got some more rules to do yet. We've got the e to the x function, its derivative. What about 2 to the x, general exponential functions? They're a little different. We need to do those. We also have the logarithmic functions and the inverse trig functions, the arc sine function or inverse sine function, for instance. So we've got to find the derivatives of those. But before we go on and do those, we want to take a look at a very important rule in the next lecture. We're going to look at the chain rule, and then after that we'll be able to look at something called implicit differentiation. Those will open Pandora's box, if you will, for finding derivatives. They open so much for us because the chain rule deals with the composition of functions. And so once we combine functions by composing them, plugging one function inside another. We do that all the time. We will be using those rules, the chain rule in particular, quite a bit after we introduce it in the next lecture. So be ready for that. It's going to be a very important one. But for now, make sure you review the trig functions, and from the first video in this lecture, make sure you go and prove those derivatives for those 3 other trig functions for your homework. Okay.